how do you represent a graph? Right? Because you want to start working with graphs now, which means that you need to figure out a good data structure to represent these. But even before we get to a data structure, some way to capture that a node is connected to another node, like A is connected to B, B is connected to C, C is not connected to A, and so on. So, how do you capture these? We need to go in, we need to figure out how we can computationally represent these graphs. So, the first and the simplest way to represent a graph is a simple edge list. Okay. So, here we have a directed graph where there is a notion of a source node and a target node. So, you have A connecting to E, that is captured here, and then you have A connecting to C, that is captured here. So, every single edge is captured by an entry in this edge list. This is literally a table which contains source and target. So, in this graph, how many ever edges you have? 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 different edges being captured through this edge list. So, you have then B connected to A, then D connected to B is here, and D connected to C is here, E connected to F, D connected to F, D connected to E, and B connected to C, and also D connected to B. Okay, so, you have 9 different edges in this simple directed graph, and we have now enumerated all of these edges. So, these are all captured in the edge list. The edge list is but the simplest way to represent a graph. So, suppose you have to create a network and share it with a collaborator. One of the most straightforward ways to do that is just an edge list. It is a very compact representation, may not be efficient. We should stop and think about it at some point of time, but it is a pretty compact representation because it just captures essentially all the nodes and all the edges. But there are challenges with this representation. You can imagine that suppose I have to find out if A and D are connected. I would have to step through the entire graph and find that there is no reason for it to be sorted. It is just sorted here for convenience, but an edge list does not necessarily need to be sorted even. So, if I am going to find out if A is connected to D or not, I am going to have to look through the entire graph, which means I have to iterate through all the edges and check if it is the A D edge, and if not, and if I finish the iteration without identifying this the existence of AD, I then conclude that there is no edge between A and D in this graph. So, this is an edge list representation. The next is that of an adjacency list. So, here for the same graph, you just list all the nodes that are adjacent to a given node in a list. So, this is these are lists. So, you can think of them as even in a Python list, right. So, it is an array of nodes, or it is a list of variable size that just tells you that D, from D you can reach B, C, E and F. From C you have no outgoing nodes at all, right, and so also from F there is no other place you can go from F, right, whereas from E you can go to only F and so on. So, basically for every node, so this is going to be another sort of table. In fact, in Python you would like to store this as a dictionary of lists. So, your key is going to be your source node and your value is going to be the list of nodes that are reachable or connected to, or you have a directed edge from the source to these target adjacent nodes. So, they are target nodes or they are adjacent nodes to your source node. I hope that is clear. This is one representation. You can obviously see that this has some advantages. Now, it is very easy to find out if A and D are connected or not. I just query the dictionary, I get a list, I just check whether my D is present in that list or not. My list is going to be CE if I am going to look at, is going to be CE if I am going to look at the adjacency of A, and I immediately can figure out that D is not present there. So, you can start thinking about what is the efficiency. And typically we say that there are n nodes, m edges in the graph. So, what is big O of n, what is big O of m, and so on. Okay. So, for example, in an edge list, to find out if A and D are connected, it takes big O of m. You need to step through all the edges in the graph. Whereas here, it is going to be much faster. It's going to be almost constant time. It really depends upon what is the size of the largest list. So, that's about what it takes to compute whether D is present in the adjacency list corresponding to A or not. Okay. But then, do you want to make it faster? How do you make this faster? How do you make this faster? You can actually use something known as an adjacency map, wherein you can actually make this a dictionary. So, you can just say, so this is going to look like, I am going to use Python speak here. So, it is going to be A, C comma E, for an adjacency map, it will end up being something like A, so what is happening here? You can just query the dictionary for A and then immediately check if D is in the dictionary, which is a very fast instantaneous query, right. So, all your queries are, most of your queries are going to be constant time queries when you have an adjacency map. So, we have looked at three simple data structures. So, one is an edge list, just like the simplest but somewhat inefficient, adjacency list, which is fairly convenient, fairly efficient, and adjacency map, which is probably one of the most efficient ones. There is also another nice mathematical representation, which is basically an adjacency matrix, where you can just represent it by a matrix of size n cross n with m non-zero entries. So, what is this matrix? It captures whether there is an edge from I to j. So, if Aij is non-zero, you know that there is an edge from I to j. If Aij is 0, you know that there is no edge connecting I and j. So, if I have to find out if A, D are connected, again it is a very fast instant process here. I just go to the row corresponding to A and the column corresponding to D, and I find out that there is no connection between A and D. So, you can see that there are 9 non-zero elements in this graph because there are 9 edges. You can see that this matrix is not symmetric in the case of a directed graph, unless you have an edge in if every edge is there in both directions, right. So, if you had all of these edges too, then you will have a symmetric matrix. In the case of an undirected graph, you typically have a symmetric matrix, because every edge means that when you have an edge A B, it means that A is connected to B, and so also B is connected to A. So, these are all captured in the adjacency matrix, and depending upon whether it is undirected or directed, it is going to be symmetric or typically asymmetric. So, now let us look at some very interesting properties of biological networks. How do we analyze these biological networks? There are a bunch of interesting properties that we compute. So, these include study of the distribution of the degree of these networks, and what is something known as the clustering coefficient. Then there are other parameters, just diameter, characteristic path length, and a host of centrality measures, which all try to quantify the complexity of a network, the navigability of a network, and general characteristics of a network. So, in any real world situation, we like to bin our observations into some boxes. So, these networks look like they are random. These networks look like they are small world networks. These networks look like they are power law networks. So, these are some bins that we will try to put these networks in, and there are network models which we will compare to see if, oh, this network looks like it is random, there is really no structure in the network or whatever. This network looks like it's small world because it has certain properties which are observed in what are known as small world networks. We will get to that shortly, so on. And similarly for power law, which is a very interesting way, this is a very interesting distribution in fact, we will see shortly, which captures how there is a very skewed distribution of degrees in real world networks. And then a very important aspect of studying any network is trying to perturb it. And how do you perturb a network? You try to remove a node or remove an edge, and along with it all the when you remove a node, you remove all the edges that connect to that node obviously. And what happens to the network when you remove these? And for example, are certain kinds of networks more resilient to attacks or failures? So, failure is typically a random node failure, suddenly a node fails, drops off the grid. In an attack, there is a targeted attack of certain nodes, right? You may have someone deliberately doing a malicious attack on particular nodes in a network or things like that, right? So, how do you understand the effect or the vulnerability of a given network to these kinds of attacks? So, these are very interesting questions that we will discuss a little later on in the course. We will also look at network motifs, which are essentially groups of nodes which are connected in the same pattern and so on. These have very interesting implications for the function of biological networks and things like that.